DNA extraction out of an agarose gel, you likely want to use low melting point agarose. This is going to allow you to actually cut out your band of interest, melt the gel around the band, and basically melt all that sugar gel away from your DNA that now has been size selected and purified with your gel. So this low melting point agarose is really great because basically what happens is you can melt it without melting your DNA, so without getting your strands to come apart. So here is more on how it works, how to use it, etc., etc., etc. Let's go.
So in order to understand how we can melt agarose, we need to understand what agarose is. So agarose is made up of these polysaccharide chains. So poly, many, saccharide, sugar. And so it's made up of these polysaccharides. So this repeating unit of these disaccharide called agarose. So di, two saccharide sugars. So each of these strands in agarose is about 400 of these agarose units, so about 800 of these individual sugar units. You have these long strands, and when you dissolve the powder, the strands are going to get surrounded by water, and then they're going to, when you heat it up, and it's going to help it dissolve and get all surrounded by water. But when it happens, it's going to kind of just like exist as these random coils. But then when it starts to cool, those coils are going to pair up into these helices. And then when it cools further, those helices are going to bundle up, and you get these helices with these like frayed ends. And these frayed ends can kind of interact with one another. End result is you get this mesh. So you get this interconnected network of agarose with these spaces inside that are filled with water. And it's these spaces inside that your DNA can then travel through when you run one of these agarose gels. Your DNA can travel through and get tangled up in it. And the longer pieces are going to get tangled up more. And so when you stop the gel running, they're going to be higher up in your gel. And so, yeah, the negative charge at the backbone of the DNA is going to give them the push that they need to get through, because at the other end, you're going to set up your power box so that you have an electrochemical gradient. And at this other end, you're going to have a positive charge that the negatively charged DNA is going to be attracted through to. And the longer pieces are going to get tangled up more and thus travel more slowly. And we can make gels with different percentages of agarose. So the more of this we have, the more of a tangly yarn we can have, or a tangly mesh we can have. A really important thing about this is that these interactions are all going to just be based on these partial charge interactions. When you have an agarose gel, unlike when you're running like a page gel, when you have an agarose gel, those interactions between this mesh, it can be undone by melting. Whereas with an SDS page, or with just a urea page, or just a TPE page, with one of these page gels, because these gels are actually formed by cross-linking these chains. So you have these cross-linked on this polyacrylamide network. And so this is going to be a really strong network. And let's talk more about the different kinds of bonds, how these are made up of covalent bonds, and these are here the mesh is made of these like hydrogen bonds between the strands, which are non-covalent, so they're not strong, or they're not as strong, and thus you can melt them. So I like to think about the agarose gels as being kind of like a knit scarf. So you have each of these strands, which are kind of like strands of yarn, and then you can knit them together. And if you know, if you've ever tried knitting, you can also pull things apart, hopefully purposefully. But the basic idea is then you can unknit this gel, and you can melt it to get your bands out of the gel. And so there are times when you would want to do this. So a lot of times when we're running an agarose gel, we're just doing it to take a look. So we can use like fluorescent dyes that I was talking about the other day to actually stain the products, or stain whatever we were getting a look at. And so this can be good if you're just wanting to see, okay, well, do the products look like they're the right size? Are there products or not from like say a PCR reaction or something like that, where you use primers, so these little pieces of DNA that target specific regions of DNA and amplify the region between them. So make lots of copies of the region between them. And then you can run a gel to see if those copies, if the region looks like it's the right size or if the region was there or not. And there are different times you might want to do this. There are also times when you might, though, want to take a look, or I mean, not though, but sometimes you just want to take a look. Sometimes you actually want to get these pieces out. And so a great thing about this gel is because it's separating things by size, well, now you can actually take those separated pieces out. This can be great, say, if in your PCR reaction, your primers weren't specific enough. So these are going to bookend the regions you want copied. If they bind to the wrong place, now you can have the different sized pieces get copied corresponding to different regions, which isn't what you want. You can also have these primers form like these weird like dimerize with each other and form these like shorter products. You can get rid of the primers using like a PCR purification kit, which are these little column-based methods, and those primers aren't, they don't like bind to the columns well enough, and so you can wash them out, whereas your DNA will get stuck, and then you can like, yeah, various things, and more on that in another post. But basically, you can get rid of the primers. So you don't need to do a gel purification if you just need to get rid of little primer products, the primers themselves, or they might not even be a problem for your reaction, whatever, depends on what your follow-up is. But sometimes you might have multiple products and you'll need to purify out yours. Another time you'll need to do gel purification is if you're doing a restriction cloning based method where you have a plasmid, so a circular piece of DNA, and you want to cut something out of the plasmid, say the cDNA for making a certain protein, and stick it into another plasmid. You can do this using restriction enzymes, but you need to, when you cut these, so these restriction enzymes are going to recognize specific DNA sequences and cut them. But so you can cut your plasmid to give you like two pieces, so your insert, the thing you or what will be the insert thing you cut out, and then the backbone that you want to and so you want to like purify the backbone from one and the insert from the other, and then mix them and ligate them, so stitch them together. But you're gonna have to purify out those pieces. So those are some reasons why you might want to do like a gel extraction. Unlike what I talked about, so the other day I talked about how we can do gel extraction, such as from these TBE gels, using a method called like the crush and soak method. You can also use this for DNA gels, but DNA gels, you can often, if you use low melting point agarose, you can just melt the agarose. So yeah, so with the polyacrylamide gel, because you have that strong network, that strong gel, you can't just melt the gel around it. Instead, you have to use things like crushing, so like manually breaking up that gel and freeze thawing it so that you're weakening the gel network, and then waiting for your DNA or your RNA to actually like diffuse out of the gel. So this can be a long, tedious process. But because you have that really strong gel, you can't just melt it around the DNA. But you can if you use a low melting point agarose. So why you need the low melting point though is that if you just use normal melting point agarose, in order to get the agarose hot enough to melt, you're going to end up melting your DNA, meaning that the strands are going to come apart. So it sounds kind of weird to talk about melting DNA. But we actually use that term when we talk about like PCR. So in PCR, how it works is that each cycle you raise the temperature to about like 95 degrees or so. And this is going to separate the strands. Then you anneal it, so you lower the temperature so that the primers can bind, and then you extend it. So you raise the temperature a little so that the DNA polymerase can then copy the strands starting at the primer, and they'll end up, the first cycle, they just end where they end, but then they'll end at the end of the template because of the way, like the first strand becomes the second strand, and more on this in the PCR post, but it's easier to explain with just the figures. But you have to raise the temperature in order to get these strands to come apart. The more temperature the molecules have, the more wiggly they are. It's going to be harder to melt these whole strands, like products than it is to like melt the primer off. And so you might see when you're like ordering a primer, the TM or the melting temperature, that's for the primer. And so the primer, because it's short, it's going to take less energy to get it to melt off, which is why we need to lower the temperature in order to get those lower the temperature further in order to get those to anneal. But we have to raise it higher in order to melt the strands apart, to get them to come apart. When we're purifying DNA out of a gel, we typically don't want them to come apart. We want to keep those DNA strands together. And so in order to prevent them from coming apart, we need to make sure that when we're melting the gel, we're not melting the DNA as well. If we were to use normal agarose, then you would be melting your DNA. And so this is why you might want to use low melting point agarose. There are also other times you might want to use it, but this is a key one. For low melting point agarose, it only needs to get to about 65 degrees Celsius in order to melt. And this is going to allow you to melt the gel around your DNA. And then just like use it, there's like kits and stuff you can use. And it makes it a lot easier than waiting for the DNA to diffuse or just like randomly travel out of the gel. So how does this work? It works by having this modified form of agarose where you weaken the interactions between those different strands. So we need to understand where these interactions are coming from. These interactions are coming from these OH groups mainly. So and the partial charge interactions between them and these things called hydrogen bonds. So just a quick refresher is that each of these atoms, so these individual oxygens, carbons, hydrogens, these are all made up of smaller parts called subatomic particles. And some of these are charged. So in your nucleus, you have the central core of the atom. You have positively charged protons and neutral neutrons, and then they're surrounded by this cloud of negatively charged electrons. Atoms share pairs of these electrons to form what we call covalent bonds, which are these strong bonds. So when you see like these lines drawn in these diagrams, these are all representing these strong bonds. And so these are the kinds of bonds that are holding together these chains, and they're the kind of bonds that are holding together the polyacrylamide in the polyacrylamide gel, those bonds that we can't just melt away easily. But there are other types of like bonds and attractions that can form between molecules that aren't based on actually sharing pairs of electrons, but they're based on partial charge attractions because opposite charges attract. When you have atoms sharing pairs of electrons in a bond, in a covalent bond, they don't always share fairly. And so with oxygen, in water, you have two hydrogens and an oxygen. The oxygen is what we call electronegative. It's an electron hog. It's going to pull the shared electrons towards itself. Because these protons are stuck in place over here, now this is going to be positively charged and this is going to be negatively charged. But these are only partial charges, not full charges, because you still have an even number overall of protons and electrons. They're just unevenly distributed. And we call this uneven distribution of charge polarity. A special case can happen in the case where you have hydrogen attached to something that's electronegative, like an oxygen or a nitrogen. And then you have, so that will form as your donor, and then your acceptor is going to be a lone pair of electrons, so an unpaired pair of electrons on an oxygen or a nitrogen or something similarly electronegative. And so this is just hydrogen bond is a special type name we give for those specific case of this partial charge attraction. And we see it a lot in biochemistry. It's what allows for the specific like base pairing between the letters of the strands of DNA and RNA, and it's the structures of the peptide backbone and all sorts of things. And in the case of our agarose, this is going to be these hydrogen bonding interactions between these different units are going to form the mesh. But So if we want to prevent the mesh from being as tight, if we want to weaken those interactions, we can then modify the agrobio so that there's fewer of those OH groups, or that they're further from the main part of the sugar. So methyl groups, if you replace these OH groups with methyl groups, so these CH3 groups, well, now you don't have that possibility for the hydrogen bond. Or you can use a hydroxyethyl group. Here you still have that OH group, but now it's further away from the core of the sugar, and this is going to weaken the interaction. You're not going to modify all of these because you still want there to be a mesh formed, but you do want to weaken the mesh. So it's important that we still have the mesh, because we don't remember that's what's going to be good to separate the strands. We just want it to make it easier to unknit the yarn, not to prevent the yarn from knitting. But you are going to see a slight difference in how your DNA products run. They're going to run faster in this low melting point agarose, and so you're going to want to decrease the voltage when you run it. And you're also going so that you still give the DNA time to separate. You might think, okay, well, fast is great, right? Things are going to go quicker, but you're also going to lose resolution if you don't lower the voltage. And also, if you don't lower the voltage, you might overheat your gel, and that's not going to be good, because then you are going to melt your gel while you're running it. And the point we want is to melt it after we run it and after we cut our band out of the gel, because the whole point of running the gel was to isolate the specific products. A cool note about agarose is that it has this thing called thermal hysteresis, which means that it melts at a higher temperature than it gels. And this can basically means that end result is that you have to cool when you melt it, in order to get comfy into that knit mesh. You get it to around 40 degrees and it'll form this gel. But now it's really comfy. And so in order to get it to unknit itself, you have to get it all the way up to about 90 degrees Celsius for normal agarose. And about 65 degrees Celsius for low melting point agarose. So this is cool because the sol gel transition, it's not the same point. So you have two different points, unlike a normal melting temperature for something. Here you have this difference in temperature, and it has this cool word thermal hysteresis. And more on that in another post. When you are making a low melting point gel, so typically what you do is you just practical wise, so you have this agarose powder, and then you melt it or you dissolve it. So you put it in your TAE buffer, and you heat it up in the microwave, and you mix it and stuff. You want to let it cool down to about 60 or 70 degrees before you pour it. Once you pour it, so you pour it into your gel and your casting apparatus, you want to let it set, so you can see it'll kind of get cloudy. When you're using the low melting point, then you want to stick it in the cold room, essentially overnight, once it sets, and you're able to move it without it doing all weird pouring off or whatever. It's still not fully set, and so you want to let it fully set, such as by sticking it in the cold room overnight. And so it's going to take longer for these gels to set. I learned this the hard way in undergrad when I accidentally poured a low melting point agarose. Didn't realize it was my first time running one of these gels. And I was like, why is it so weak and fragile and it's not setting? And I was thinking how do people run these gels all the time and not just get so super frustrated, and how it seems so hard? And then I realized that it was the low melting point. So read the bottles, and when you're running one of these, or when you're pouring one of these low melting points, know that it will take longer, that your gel will be more fragile. And so take caution when doing that. Okay, and just a final note is, or I guess a couple of final notes, agarose, we also use it for other things. So gel filtration columns are often made of agarose. And one of the reasons why we use it for that and for this DNA gel electrophoresis is that it's kind of boring in that It's not like charged or anything. We wouldn't want to use something charged when we're trying to separate this DNA using charge, and we don't want the DNA to be like repelled from the gel we're trying to run it through. But the charge can be good, and or at least not bad in some cases. And so when we talk about agar, so like when we're making like a petri dish to grow bacteria on, or we're not making the petri dish, we're filling the petri dish with this agar. This agar is going to be a gel made up of agarose and agaropectin. So it has agarose in it, but it also has this agaropectin, which has modifications, including like some sulfur groups, so some like negatively charged groups. So this is going to be a less pure mixture, more variable, and also have these like modifications that might impact how your DNA would run through a gel. So you wouldn't want to use agar for one of these gels, but agar is great for making these bacterial pancakes. So hope that helped you understand how low melting point agarose works and why you might want to use it if you are going to do a DNA gel extraction.